We're going to start with one type of mechanic energy, which is a kinetic energy, the energy of moving objects. Kinetic energy, with a symbol of EK, is the energy of an object has due its motion. From a Greek word kinema, meaning motion. So an object kinetic energy is directly related to its mass, direct proportional to mass, and direct proportional with square of its speed. Here is the formula. Ek is half of the mv square. And if you take a look at the units, since the formula is with a mass and velocity square is a kilogram, is a unit of mass, and meter per second, all in the power of 2 is a unit of velocity. That makes kilogram meter per second times meter. That means kilogram times meter per second is Newton. So it's a newtons times meter. So that is equal to 1 joule, which is unit of work that we already just did. Here's a quick question to test you on a relationship between kinetic energy and speed and mass. So a car 1 has twice the mass of the car 2. So what does it mean? It means that m1 is equal to 2m2. But they both have the same kinetic energy. So kinetic energy 1 is equal to kinetic energy 2. If the speed of the car 1 is v, approximately what is the speed of the car 2? A, 0.5 of the v, 0.707 of v, the same as the car 1, 1.414 v, or twice as much as a car 1. Now, you can pause the video and try to answer this question. Now, here is what is given. Mass 1 is equal to 2m2. Speed of the car 1 is the v, and kinetic energy of the car 1 is equal to kinetic energy of the car 2. What we're looking for is a relationship of v2 with v. It's bigger than v1 or smaller than v1. Now, what is the reasoning behind this? The first thing that we have to think of is they both have the same kinetic energy. So that means half of the m1 v1 square has to be equal to half of the m2 v2 square. Now, since that we have two terms that are pretty much the same, you just get rid of those, and we have m1 v1 square is equal to m2 v2 square. But we do have another known, which is m1 is equal to m2. So instead of m1, we replace it with 2m2. And v1 is v, and v2 is unknown. So now we have everything. We just have only one unknown, is a v2. So from here, v2, 2v square is equal to v2 square. Then you square root both of them. Then we have v2 is equal to square root of 2v square, and v square comes out of the square root. We have v square root of 2. That is equal to 1.14 v. So the answer is D. If you did this, you are right, and you have a good understanding of kinetic energy. When we talk about work in a previous lesson, we said that the definition of the work is a change in energy. And the definition of the energy is ability to do work. So you see very clear that between work and energy, there is a relationship. Now we're going to talk about work-energy principle, that relationship. Work-energy principle says that the net amount of mechanical work done on an object equals to the object's change in kinetic energy. But how to prove it? Here it is. The work formula is force times displacement. But based on the second Newton law, force is equal to ma. So we replace F net with ma in this formula, and we get ma delta d. So then we can go back to kinematics in equation number 4, and we can say that V final square is equal V initial square plus 2a delta d. Now, if we move V initial to an other side of equation from positive, that will become negative. So that's why we have V final minus V initial. And what is left on this side is 2a delta d. Now, if we multiply both sides of the equation with m, you're going to have m 2a delta d equals to m V final square minus V initial square. Next step would be, what if we take that equation and we divide by 2? If we divide by 2, then we have the first left side is going to be m 2a delta d divided by 2, and the second one, the right side, is going to be m times V final square minus V initial square divided by 2. So if you see that 2 and 2 cancel, and what is left there is ma delta d. So it's ma delta d. So ma delta d is net work. On the right side, we can actually multiply by m. So m V final square divided by 2 minus m V initial square divided by 2. So next step would be, what is ma? Is force. So force times displacement is equal to m V final square divided by 2 minus m V initial square divided by 2. This formula in a red box, as it is very important because it has a lot of application when you solve problems. However, we can just look for more. Kinetic energy, from that definition, from the formula, is a half of the mv square. And if you replace that m final square divided by 2 with a ek final, so final kinetic energy, and if we replace m v initial square divided by 2 with initial kinetic energy, we get something like a F net is equal final kinetic energy minus initial kinetic energy. Or, you know that everything is changed, you can replace it with delta. So, net work is equal to change in kinetic energy. And that's what we said. So WorkEnergy Principle says that net amount of mechanical work done on an object is equal to object's change in kinetic energy. And especially this formula is very important. But you're going to see this has its own application, or even this, the last one, has its own application to solve the problem. Understanding the concept without practice, it's not possible. So that's why all the time we practice. We try to solve problems in order to enforce the learning, enforce understanding. Let's try one. You pull the sled with a mass of 80 kilogram with a force of 180 Newton at 40 degrees above the horizontal. The sled moved 5 meters horizontally. So delta x or delta dx or delta d is equal to 5 meters starting from rest. That is very important. Don't skip that. Starting from rest, that means initial velocity or initial speed in this case, because we are in a energy unit when we are not talking about velocities anymore. We are talking about speed. Assume that there is no friction. So that means there is no waste of work. Let's see what is given. Force is given is 180 Newton. Angle is given is 40 degree. Displacement is given is 5 meters. Initial velocity is given, that is 0. What is required is work. So to find work, what do we do? So total work is total work that you do, which is the force that you apply on x-axis on or F cosine theta time displacement, or force displacement cosine theta. It's the same thing. Now, we know that force is 180 Newton, and cosine is, theta is 40, so cosine theta times displacement, and that gives you 689 joule of energy. Next one is find the final speed of your sled. You know that the formula that I mentioned, work total is change in kinetic energy, is equal to half of the mv final square minus half of the mv initial square. So that total energy that we just calculated at A, now we have no choice but to use it. So we know that V initial is 0. That makes the whole component 0. So what is left on this one is half of the mv square. Now we solve for V final square, which is 2 times total work divided by mass. Now we can square root it to solve for V final, and we plug numbers, and the answer is 4.15 meter per second. Here is another practice. A 150,000 kilogram rocket is launched straight up. The rocket engine generates a thrust of 4 times 10 to the power of 6 Newton. What is the rocket speed at a height of 500 meters? What is given? It's a massive rocket. It's 150,000 kilogram. Thrust is 4 times 10 to the power of 6 Newton. Delta y is 500 meters, and final velocity is required. Remember, the engine the rocket start from rest. So initial velocity is 0. Now let's do work energy principle. So net work is equal sum of all work done by forces is equal to change in kinetic energy. So let's start work done by which force? Force of gravity, for example, is a force of gravity times delta y cosine angle between those two, which is 180. Now, how do we know that it's 180? Here is a displacement. If you move the displacement parallel to itself, it's going to be here. So that means they are at a straight line, but in opposite direction. So that means the angle is 180 degree. And cosine of 180 degree is -1, which make that work negative. So it's a negative times mass times gravitational acceleration times displacement will give you a negative 0.74 times 10 to the power of 9 joule. We leave it to times 10 to the power of 9. We can do it 7.4 times 10 to the power of 8. But you're going to see that the order of magnitude of the other one is times 10 to the power of 9. So let's do a thrust. It's a force times displacement times cosine theta. But theta between displacement and force is the same direction, parallel to itself. That means the angle is 0. And cosine 0 is +1. So that makes the work positive. If you plug those numbers, 4 times 10 to the power of 6, 10 in the power of 6, 500, that will give you +2 times 10 in the power of 9. Now we are ready to do sum of those two, which make that F net, which F net is equal to change in kinetic energy. That's what we're looking for. We're looking about V final. So sum of those two, one positive and one negative, so that means it's the difference of those two, is 1.26 times 10 in the power of 9 joule. Now we are ready to apply that work energy principle. So changing kinetic energy, which is half of the m v final square minus half of the m v initial square, is equal to sum of those two that we just already calculated. Now, after knowing this, we can solve for v final because v initial is already 0, so that component here is gone, is 0. So what is left is v is 2 times changing kinetic energy, which we already calculated, which is equal to net work, divided by mass, and we square root it. So then you plug numbers. What do we know? We know 2 times 1.26 times 10 in power of 9 joule divided by 150,000 kilogram. And the answer would be 129.6 meter per second. Imagine, after 500 meter, the rocket reached 129.6 meter per second, almost 130 meter per second. And if you multiply that by 3.6, you can find what is speed in kilometers per hour, and you can compare it with an airplane or a train or a car, how fast the rocket actually can reach that speed just in 500 meter. This is section 4.3, gravitational potential energy. This is another type of mechanical energy. Now we're going to shift our attention to another type of mechanical energy, which is a gravitational potential energy. There's a worker there that is lifting the crate. So the worker apply a force to lift it, which is against the gravity, which is equal to force of gravity, which is equal to mg. So we know that work done by applied force is equal to force times displacement times cosine theta. But let's analyze it. Force is force that is against gravity. So it's a normal force, but is the same as a force of gravity in this case. Now, displacement is delta H, so it's a change in height. And cosine theta, the theta is 0 because direction of the applied force and direction of displacement is the same. So that means the angle is 0, cosine of the angle is 1, so that 1, you don't ever write it. So the work is equal to mg delta H, which, as we know, work is equal to a change in energy. So we're talking about change in gravitational potential energy. So we came up with this formula. Change in gravitational potential energy is equal to mg delta H. Or sometimes delta H and delta Y is interchangeable. You might have seen this as mg delta Y as well, so that is correct as well. Gravitational potential energy is energy possessed by an object due to its position relative to a surface of the Earth. So that means the higher from a surface of the Earth, the more energy. So that's why, if you know, we build dam on a hydroelectric power plant to make the water to raise up as much as we can. And then we can put turbines at the bottom of the dam, so the water is going to fall down with an enormous energy because of the gravitational potential energy. And later on, we're going to see that that gravitational potential energy is transformed into a kinetic energy of the moving water, and that is going to be transformed into a kinetic energy of the moving turbines, and then it's going to be transferred to electric energy. So it is because of its position. The higher the position, the higher the gravitational potential energy. Now you see that from formula though. So the higher the gravitational potential energy, it means that higher the mass, the higher that height. because G on a same location is constant, so it depends on mass, gravitational acceleration, and height. Now let's see the units. Units as energy should be equal to work, but let's check first. The formula is mg delta h. So unit of mass is kilogram, unit of g is acceleration, gravitational acceleration is meter per second square, and unit of height is length, it's a meter. So kilogram meter per second square is Newton times meter. That is exactly what we talk about work. So unit of work is Newton times meter or joule. So unit of gravitational potential energy is joule. Now we're going to talk about gravitational potential energy and reference level. So when we talk about gravitational potential energy, we talk about dependency. So gravitational potential energy depends on a mass, gravitational acceleration, and height. But height relative to what? Height higher than a desk, higher than a floor, higher than the ground. Everything is relative. So a reference level is a designated level to which the object may fall. That is the potential of fall, because that's what we call potential energy. There is a probability there, there's a potential, there's a stored energy. If that is falling, then the potential energy is released. It's the same thing as a chemical potential energy. If the reaction doesn't happen, that energy will not be released. So that's what we call gravitational potential energy of the object due to his position from the level that it may fall. So at gravitational potential energy at that level is considered to be zero. But remember that it is relative. So gravitational potential energy is a relative energy. It depends on a reference level. So if the textbook on a desk, then we can say that gravitational potential energy is zero relative to desk reference level. However, imagine if we remove the desk, what is going to happen to textbook? It's going to fall, and you're going to see that it's going to fall, and it's going to fall fast, and it's going to hit the floor, and you're going to hear that sound. So gravitational potential energy is transformed to a kinetic energy because it's moving, and then it's going to transform into a sound energy and heat energy, thermal energy. So you see the energy transformation right there. However, let's go back to the point, to reference level. If the skiers cannot let it go, it is not going to move. It's not going to have a kinetic energy of the moving, but it is going to move fast because its position and gravitational pull is going to pull him down. Same thing is for a hammer on the lower right diagram. The hammer is going to hit the nail. So it's going to hit the nail, and that gravitational potential energy is going to be applied to a nail. And that is going to be the lowest potential energy at the reference level. As I often say, the practice is the best way to enforce understanding. This time we'll do some practice with the gravitational potential energy. A 58 kilogram person walks down the flights of stairs shown. Use the ground as a reference level. Calculate the person's gravitational potential energy at the top of the stairs, on the landing, and on the ground level. So we have everything. We have a mass 58 kilogram. We have height at the top of the stairs, which is a 6 meter. At a landing, 3 meter. And at the ground level, 0 meter. And what is looking for is a gravitational potential energy. So formula is mg delta h. And then we can start one at a time. Let's say at the top of the stairs. So h at the top is 6. So 58 times 9.8 meter per second times 6 meter equals 3,410 joule. Now landing is 3 meter below, so half of the energy, which makes 1,705 joule. And the ground level is 0, height. So if you multiply 0 with any number, it will give you 0 anyways. But take a look. So as you go from top to bottom or from bottom to top, you're going to see that at the top is a higher up. So you can see that is actually have this biggest amount of gravitational potential energy. So at the down middle one is going to be half of the gravitational potential energy, and at the bottom is 0. As you're moving from bottom up, as you're moving higher and higher from what we call as a reference level, the gravitational potential energy is increasing. So that's how you see the relationship between gravitational potential energy and the height relative to reference level. This is a last practice problem with gravitational potential energy. 40 3-kilogram blocks, 20 centimeter thick, are used to make a retaining wall in a backyard. Each row of the wall will contain 10 blocks. You may assume that the first row of blocks are placed at a reference level. How much gravitational potential energy is stored in a wall when the blocks are set in a place? So what we have here is each block is 3 kilogram. The height is 0.20 meter. Number of blocks are 4 times 10, which is 40 blocks. So they are set in 4 rows. And gravitational potential energy total is required. Let's start one row at a time. The first one is formula is mg delta h1. So we have 10 blocks with 3 kilogram times 9.8 meter per second square times the height for the first one, since that are placed in a reference level at the ground. They cannot really go like lower than that, so that means it's going to be 0. So everything is 0. Next one, same formula, mgh2 delta h2. Now we have 10, another set of 10 blocks times 3 kilogram times 9.8 meter per second square. But now those blocks are actually placed on the top of the first layer, first row. So if they fall down to the reference level, they'll fall down from the 0.20 meter. So that means that height, change in height, is 0.20 meter, and that will give you 58.8 joule. We'll do the same for the third layer, third row. That is mg delta h3. Now this is going to be from 0.4, so that's why we have delta h 0.4 meter here. That will give you 117.6 joule. And the last one, which may fall from the height, which is 0.60, then you can just use that 0.60 here, and we get 176.4 joule. And total is going to be like add of all, so 0 plus 58.8 plus 117.6 plus 176.4 joule is equal to a 352.8 joule total. Just a very quick reminder that when we talk about potential energy, we're talking about energy that is potentially released. So gravitational potential energy is the energy because of its position. So it doesn't mean that energy is going to be used, but it is there. And if that object falls down to a reference level, then that energy is going to be released and transformed to another type of energy. However, potential energy, it is in a form of different type of energy, and I can mention like a couple of them. The chemical potential energy is stored in a food that you eat. So during the work, an elastic band, by stretching it, store elastic potential energy. So another potential energy is elastic energy. We are going to look at this type of energy later on. Battery contain both chemical and electric potential energy. So that means that the battery, the potential energy is there, electric potential energy is there. But if you want to try it, test it, so you have to have a load or something, a device to consume that electric potential energy. So potential is there to do some work, but has to be a device to use it. That's the whole idea about the potential. So it's there, but needs to be used at some point. And that's about it for gravitational potential energy. And have a good one.